You do it, I do it, we all do it dozens of times a day. You type a question into a box and poof, the perfect answer appears in a split second. It honestly feels like magic. But it's not. It's some of the most complex, most fascinating engineering on the entire planet. And today, we're going to pull back the curtain and show you exactly how it works. I mean, stop and think about that for a second. It's wild, right? You have this kind of vague idea in your head, and somehow a machine not only understands it, but it sifts through literally billions of pages and ranks the very best ones just for you, all in less time than it takes to blink. This whole incredible process has a name: information retrieval, and we're going to break it down step by step. Okay, so the very first thing you have to get your head around is this really crucial difference. Finding a vague idea is a totally different ballgame from finding an exact file. And search engines, they were built to solve that messy human problem of finding ideas.
In this slide really nails the two worlds, side by side. On the left, you've got data retrieval. Think of it like telling a warehouse manager, I need box number 101. It's precise, it's a command, there's one and only one right answer. But information retrieval, over on the right, that's like walking up to a librarian and saying, I'm looking for books about famous German scientists. Your request is fuzzy. The goal isn't one perfect match, it's a helpful, ranked list of the best possible matches.
And that, right there, is the core challenge. Information retrieval isn't about finding exact matches in some nice, clean database. No way. It's about trying to understand an information need inside the messy, chaotic world of human language. The entire game, the whole thing, comes down to just one word: relevance. So how on earth can any system possibly do this? Well, the secret is that it does all the hard work in advance. Long before you ever type a single word, the search engine has done a mind-boggling amount of prep work. It's like organizing a global library before the doors even open for the day. This is what we call the offline phase. So this prep work kicks off by analyzing all the text. First, the system tokenizes every document. That's just a fancy way of saying it splits them into individual words. Next, it gets rid of all the useless little stop words like the, is, or that just create noise. And finally, it does something that is absolutely crucial for understanding meaning, a process called stemming. Stemming is really just chopping words down to their shared root. And the goal is super simple. You want to teach the system that words like computing, computer, and computed are all just different flavors of the same core idea. It's the reason you can search for run shoe and still find pages about running shoes. And the results is, well, it's pretty fascinating. On the left, you have normal human language. On the right is what the search system actually sees. To us, it looks like total gibberish. But by chopping retrieval and retrieving down to the same stem, retrieve, the system can now connect related ideas way more effectively. So after all that processing, what do you get? You get the system's master key, the inverted index. It's just like the index at the back of a giant textbook. It's a massive map where every single word stem instantly points to every document that contains it. This, right here, is the secret to how it can search billions of pages in milliseconds. Okay, so all that massive prep work is done. The digital library is perfectly organized. Now, it's your turn. The moment you hit search, the system just springs into action. Here's the incredible journey your query takes. So first, your query gets the exact same treatment as all those documents. It's tokenized, cleaned up, and stemmed. Then, the system uses that super fast inverted index to pull up a list of every single document that contains your search terms. But here's the problem. That list could have millions of matches. Which brings us to the most critical step of all: ranking, deciding which page actually deserves to be number one. This is it. This is the secret sauce. Ranking is what separates a great search engine from a completely useless one. It all comes down to scoring, and the foundational idea behind it all is actually surprisingly simple, and it dates all the way back to the 1950s. An information retrieval pioneer named Hans-Peter Lahn came up with this revolutionary idea. The number of times a word shows up in a document is a pretty big clue about what that document is about. I mean, it makes sense, right? This simple concept is the bedrock of how search engines figure out relevance. This gives us the first half of our scoring formula: term frequency, or just TF. It's really just a count. If you search for black hole, a document that says black hole 20 times is probably more relevant than one that only says it once. Simple enough, right? But here's where it gets really clever. The other half of the equation is inverse document frequency, or IDF.
This basically measures how special a word is. Think about it. The word the is in almost every document, so it's not special at all. But a word like exoplanet, that's rare. Finding that word is a very, very strong signal that the document is highly relevant to what you're looking for.
And the magic happens when you combine them. The final relevance score, called TF-IDF, is calculated by simply multiplying the term frequency by the inverse document frequency. So the highest scoring pages are the ones that use a term a lot, that's a high TF, that is also a very rare and special term overall, a high IDF. This was the breakthrough that turned search from a simple matching game into a true relevance engine.
This chart shows you the power of IDF perfectly. A super common word like the has basically zero scoring power. It's useless. A more specific term like retrieval is much better. But a rare technical term like ratio, it has a massive IDF score. Finding that word is a huge signal that you've probably struck gold.
Now, ranking individual documents is powerful, for sure. But modern systems go even a step further. They actually get smarter by understanding how different documents relate to each other. And this is done through a process called clustering. The idea behind it is so simple and intuitive. It's called the cluster hypothesis. All it says is that if you've got a bunch of documents that are really similar to each other, they probably answer the same kinds of questions. It's just like putting all the cookbooks in one section of the library. So one really fast way to make these groups is with something called a single pass algorithm. Here's how it works. The system grabs document 1 and says, okay, you're the start of cluster 1. Then it looks at document 2. Is it similar? Yep. So it joins that first cluster. But, oh, document 3 is pretty different. So it says, okay, you're going to start a new group, cluster 2. And then document 4 comes along and it's similar to that second group, so it joins in. This process just keeps going, sorting the entire collection one document at a time. So there you have it. That's the core of how search works, breaking down language, building a massive index, and scoring for relevance in the blink of an eye. We've spent decades absolutely mastering the art of finding documents, but the next great frontier is teaching machines to truly understand them, to read them, synthesize them, and answer our questions, not with a list of links, but with genuine knowledge. The shift from just finding pages to actually understanding information, well, that's already happening, and believe me, it is going to change everything.